Welcome. We're going to dive into a really cool topic today, the one fundamental trick that lets computers see. We're talking everything from your phone to a self-driving car. And you'll see how this one simple idea is the absolute root of some of the most revolutionary tech out there. Okay, so let's start with a big question. You and I, we look at a road and we instantly see the lines, right? It's automatic. But how does a machine, say a self-driving car, how does it see that exact same thing? Well, here's where it gets wild. A computer doesn't see a picture. Not at all. To a computer, an image is just a giant grid of numbers. Every single number just represents the brightness of one tiny pixel. So the real puzzle is, how in the world does it find a line in that massive sea of data? The answer is actually surprisingly simple, and honestly, pretty elegant. Computers don't look for the line itself. They learn to see by finding the edges first. So what is an edge? It's just a boundary where the brightness of the pixels changes really, really fast. Like the outline of an object. This is the very first, most basic step a computer takes to start making sense of the visual world. Okay, so the computer's job is to find those spots with a sharp change in brightness. But how does it do that? What's the math? Is it magic? It's not magic, but it's close. The secret sauce is a process called convolution. Now, that sounds super complex, I know, but just think of it like this. You're sliding a tiny, special magnifying glass over every single part of the image, and this little magnifying glass is called a kernel. And this whole process is just a few simple steps, repeated thousands of times. The kernel slides over a little patch of pixels, it multiplies its own numbers with the pixel values right below it, adds all those results together, and creates one new pixel for a new image. If that final number is big, bingo, the computer knows it's probably found an edge. And this is what one of those magnifying glass kernels actually looks like. Check out the numbers. You've got negatives on the left, 0 in the middle, and positives on the right. This setup is brilliant. If the pixels on both sides are the same brightness, the positives and negatives cancel out, you get 0, no edge. But if there's a big change from dark to light, the math gives you a big number, and that vertical edge just pops right out. All right, that's enough theory. Let's actually see this thing in action. We're going to turn this idea into reality with just a few lines of code using a really powerful and popular tool called OpenCV. And hey, don't worry if you're not a big coder. The whole thing really just boils down to 4 simple steps anyone can follow. We're going to import the library, load up our image, switch it to Grayscale, and then save the result. That's it. And here's the code itself. See? It's pretty straightforward. That first line, import CV2, is just us saying, hey, let's use the OpenCV toolkit. The next line reads our image file. Then CV color to grays does that key step of converting it to grayscale. And finally, I am right saves our new grayscale picture. It's almost like reading plain English. So you might be asking, why do we have to convert it to grayscale? Well, that's a super important prep step. By stripping out all the color, we're left with just brightness. It makes the computer's job of finding those sharp changes, those edges, way, way easier and a lot more efficient. So what happens when we combine our code with that kernel we just talked about? Well, in OpenCV, there's a function called filter2d that lets us do exactly that. And the results are amazing. Just like the quote says, all the horizontal lines pretty much vanish, and only the vertical edges, like the outline of a laptop, stay sharp. It's perfect proof that our kernel worked just like it was supposed to. But this simple method has a little bit of a flaw. It can be what we call noisy, meaning it picks up a lot of tiny, random dots and calls them edges. So it's time to level up. Let's check out a much smarter all-in-one tool. So allow me to introduce the Canny Edge Detector. Its secret weapon is that it does a critical step first. It cleans up the image. It gets rid of all that random noise before it even starts looking for edges. It's kind of like tidying up a room before you start searching for something. Okay, let's put them side by side. On the left, our basic kernel. It's fast, but yeah, it's a little messy. But on the right, the Canny detector is so much smarter because it gets rid of the noise first. It gives us this incredibly clean, precise output, focusing only on the strong, important edges. I mean, you can just see the difference, right? And here's the really brilliant part. Even though there's a lot of complex stuff happening behind the scenes, noise reduction, fancy math, for us, using the powerful Canny detector is as simple as calling one function, just a single line of code. That's it. So we've gone through a lot of the tech details, but now it's time for the big question. Why does any of this actually matter? Well, it's because this simple technique is at the very heart of technology that is changing our world. Let's bring it all back to where we started, self-driving cars. If you take away just one thing from all of this, let it be this. Edge detection is almost always the number one absolute first step for nearly any complex computer vision system out there. It's the bedrock everything else is built on. And once you know about it, you start seeing it everywhere. From a document scanner finding the corners of a page, to medical scans identifying the outlines of tumors, to robots in a factory spotting defects. But the most high-profile application, of course, is in autonomous vehicles. And this is the key. For a self-driving car, finding edges isn't just a cool feature. It is the absolute foundation of how it sees and understands the world around it. This is what allows the car to do its most critical jobs. By detecting edges, it can track lane lines to stay centered in its lane. It can see the outlines of obstacles like other cars or pedestrians, and it can even read the shapes on road signs. And that really just brings our whole point home today, doesn't it? This really simple, elegant idea of finding a line in a grid of numbers is the fundamental building block for some of the most advanced, world-changing technology on the planet. So today, we took that very first step in teaching a computer how to see. We've given it the basic ability to find a line. And that leaves us with one last, pretty exciting question to think about. Now that it can see lines, what will you teach it to see next?